Hello. And zoom. Where's Matt? Was right outside. Cool. Oh boy. All right. There's Bayless.
You're muted.
Okay.
All right, there we go. Yeah.
Actually, I'm gonna see if I can.
I'm actually going to remute just in case I mess something up while I. I think I did that right now. Yes, and I'm not echoing like crazy. And I need to do constant presence, applied layout. I think I'm figuring it out. All right. Getting there. Oh, thank you.
Oh, all my stuff is here. I'll be back.
All right, hurry. Okay, who we got here? We have Jasmine. Hello. We have. Here we have Matt. Carol will be right back. Edie and Will. We have Coleman, right? Yes. And you're Henry?
Yes.
Joining us anew. Welcome. And I shared you on the folder and documents, etc. today. If you need me to share that to a different email address, like Coleman did, just send it to me and I'll get that taken care of ASAP.
All right, we'll do.
So we are missing Callie. Jasmine, any?
Oh, there she is.
Oh, there she is. Hey, Kaylee. And Peter's right there. Jordan I talked to, he had some tech issues, so I'm wondering if we might have some problems with him today. So we are missing Jordan. And otherwise, I think we're here. Oh, and I'm sorry, and Chris. Sorry.
Yes.
Hello, Chris.
Hey.
Do you guys have a lot of ambient noise running around? If things go the way I'm hoping today, there should be kind of a fair amount of back and forth, and I'm wondering how bad it would be to just kind of be unmuted across the board.
We're quiet.
That seems okay. If there's a lot of noise outside your room, go ahead and hit the mute button. But otherwise, let's go for it. So first things first, I said in my email, I think it was Kaylee at the end was talking about like, oh, I think this might be the issue with the views, and like we shut off, and I suddenly had this thought that maybe I might have made you guys feel like when I asked you to, I had the random number generator, I was asking you to describe the videos that I was trying to like play gotcha with you on that, and I really didn't mean to make you feel that way at all, and I apologize if I did. It seemed like that was pretty likely at that moment after the fact. I had kind of always wanted to do that just because I've never done this before, and I wanted to see how you were responding to them, what you were getting from them. And as I said in my email, I was very impressed with the responses that you gave me, and it was really interesting feedback for me. So with that out of the way, and hopefully my apology accepted. Yeah, okay, some smirking. Okay. We will move on. I've gotten a lot of the worksheet zeros at this point. Please get them into me. Anybody have any problems using the equation editor? Did anything feels like difficult to you in there?
I just had a question. I couldn't remember. How exactly did you want us to turn them in? Should we just download the file and email it to you, or do you want us to?
So there's what I've said right now is that there's two options. Right now, what happens is I share a document to you like a worksheet, and or you click on the link on the assignment sheet to go to worksheet 1. Let me just do that real quick. I will share. Share Chrome. Yeah, so you could go into the assignment sheet. Let's say you're working on worksheet 1. Click on it, takes you into Drive. At this moment, actually it says it right in worksheet 1. I forgot that I added that up there. There's two ways that you can do it. You can go up to File, click Make Copy for yourself. Then you have your own version, and you could go in and, I guess what I had in my head is if you want to do scratch work on side paper or something like that, go ahead and do that. And then you could write your answers in like I've shown here in the worksheet, right? Using the equation editor. The advantages of that are it'd be clean, right? You'd be able to edit it after the fact. I would be able to go in and very specifically I can't comment on it myself right now, make comments if you made any mistakes or anything like that. So it allows for a little bit more interaction. However, if it's my first time doing this, so if that's tedious for you, if you would prefer, you could print out the document. I think I tried, in the interest of that, I tried to leave you white space to be able to do work. So you could print this, do your work, rescan it, and then what I suggested, rather than emailing it to me, is create a Drive folder entitled, like your last name _ modern homework or something like that. Share the folder to me, and you can just drop the files into that. And I will get your homeworks that way. Yeah, go ahead, Jasmine.
Is it okay if we do the work on a separate sheet of paper, or do we have to do it on that document in the white space?
It's okay to do it on a separate sheet of paper. I think that's fine. There will be, let me say this, there will be some, during the development of the quantum model unit, inside the worksheets, there will be links to virtual experiments that you can do. And in that case, you might find yourself wanting to do the work in the worksheet on the digital document. I think then it would definitely be more convenient for you. Or if you wanted to if you were plotting a wave function and you wanted to put a picture in it and you were using a web app, you could take a screenshot and just cut and paste it right into the document as opposed to printing things and dealing with all that business. Okay. One note on Google Docs.
One question?
Yeah, go ahead, Will.
Sorry, how much work do you want us to put in there if we're doing it if we're making it in Google Docs? Because I like to write a lot out, so should I put all of that in there, or just how much do you want to put in there?
Most of the problems on this first one aren't terribly complicated. So I gave this sample solution right here, right?
Okay.
T prime equals T gamma, and then I plugged in time is 0.001 seconds times 1 over the square root of 1 minus 0.9 squared equals 0.0023 seconds.
Okay.
You've written down the equation, you've said what you're plugging in, you've given me enough information to know what law you were applying and what numbers you chose to use, and then the answer that you got. So if your answer was wrong, I might be able to figure out what you did wrong. I think when we get to more complicated problems, and don't worry, they're coming, you could, this stuff's pretty simple, and you guys might be wanting something really, really intense. You might be finding yourself really wanting to be able to work by hand and have to show more work. At this stage, though, this is satisfactory to me, and I could really see you wanting to go either way with doing the work by hand or using the Google Doc method. Is that all okay to? My only concern is being too vague with you, but I'm hoping you know what you need to do. You good? Okay. the first two problems are plug and chug. I shifted the due date, though, because the second half with the DeLorean here, if you're not familiar what movie that's from, I'm going to cry a little bit, but it's cool. It's from Back to the Future. They're not hard, but the perspective and what I'm asking you to like think about might be pretty confusing, and you might want breaks from it. So I just shifted the due date a little bit on it. So let me know if you have any problems with it. You can use the comment thing. You can email me. All right. So that is coming up next. Finally, you're doing some problems. And you're meeting Jose and Hose B, who are my favorite characters.
I only got that.
And I got a little tiny laugh on the Jose and Hose B. I can't even take credit. It was a modern student from like 5 years ago. I was like, what do you guys want to name the first guy in the K frame? And they're like, Jose. I was like, what do you want to name the guy in the K prime frame? He's like, Hose B. And a little part of me died. And here we are. And now I can't stop using it. Okay. So I'm going to go back to stop sharing. So in the videos, you slogged through a whole bunch of algebra. Thank you for putting up with me. Getting to length contraction derivation. You might be wondering why length contraction was so much more involved than time dilation. And when we get to kind of our deeper conversation about proper frames, which I'm hoping we have enough time for today, I'll start to elucidate why one is harder than the other, because it's kind of a neat reason. But I want to talk about, in my sample problems, I started suggesting our first paradoxes that we encounter in relativity. That of the twin paradox, one twin departing in a spaceship and coming home and having aged less than their twin back on Earth, and that of the tunnel paradox with the weird train thing, with the tunnel is shrunk or the train is shrunk, depending on your perspective. Before I launch into that entirely, do people have any questions about things I covered in the video? Forgot the whole plural thing. Yeah, Jasmine?
It's about something you didn't really cover in the video, about the time dilation. Because the whole point of time dilation, right, is that in one frame, the person doesn't seem time dilated, but sees, like, the clock somewhere else being dilated, right?
Yeah.
So wouldn't time dilation technically happen for both frames?
Yeah,
because, like,
that's actually that. Sorry, finish
I was
the
really
question.
confused by that.
Yeah, no, that's exactly right, and that's kind of the beginning of the meat of our discussion today. That's a very good point. Like, there isn't one frame that sees dilation and one that doesn't. They see dilation of some things and not dilation of others. But yes, we will talk about that. Any other questions? Dallas.
I had a question about, you were talking about the particle accelerator going in a circle.
Yeah.
And how the particle sees it as a really, really stretched ellipse.
Yeah.
But once it turns the corner, wouldn't it see it stretching the other way?
Yeah, it would see the ellipse constantly rotating in space. And by the way, I should preface that by saying I don't think it's accurate to say precisely that the shape is truly an ellipse, but that's a generalization of it. So yeah, if here I can kind of demonstrate it with something I was going to use for something else. One of these prepared drawings. We have figured out a solution for me whiteboarding. That'll be good, but not quite yet. So if a particle was going around the edge of this circle, they would see distances parallel to the direction of travel as being contracted. So if they were going very, very fast, they would see lengths that are perpendicular to the direction of travel as having no contraction whatsoever, because it's not moving relative to them in that moment. So the width of the circle would appear to be normal if it looked to the side, but as it looked ahead, the width of the circle would be compressed. And as it made the turn, this thing would constantly rotate around, which actually makes it very, very hard to control the charge as it goes around the circle. And the very first high-energy particle accelerators were called cyclotrons, and they just used big, giant, like a huge magnet Oreo cookie. Gigantic magnet over gigantic magnet with vacuum in between, and it used this oscillating electromagnetic field to get these electrons going around in circles, but never took into account the fact that relativity was changing the shape of that device to the charge. The latest particle accelerators are called, anybody know the name? There's a chance. The Tevatron was a cyclotron. There was the next particle accelerator made by Ernest Orlando Lawrence after the Tevatron was the Beavatron, which is just hilarious. But no, there were cyclotrons, and it's okay if you don't. I'm just wondering if you've heard it in the news. Synchrotron. What do you think synchro means?
The two magnets move in sync.
It's synchronized to relativity. And so synchrotrons contort the magnetic fields that they generate because they're thinking carefully about the fact that the geometry of the device is being affected by relativity. And it wasn't until we started taking that into account that we were able to get charges up to truly stupendous velocities. The velocities that you're seeing in the Large Hadron Collider at CERN, or the Relativistic Heavy Ion Collider at on Long Island, just 30 miles from where we are right now. So there you have it. Yes, that would constantly rotate, and for old school particle accelerators, that was a limitation. Any other questions? All right. So on to okay.
In that same question with the elongated shape on the particle accelerator, was the reference frame with which it would look like that? Would that be if we were considering the particle itself to be at rest, or was it?
Yeah, if you put a chair on top of the electron and you sat on the chair.
Okay, so
you were riding the electron like a horse around the particle accelerator. The electron sees the the cyclotron as compressed.
So the compressed thing is basically moving around the particle. It's
yeah. So to us, the electron would appear like it is. Let me see if that looks like it's okay. It would look like it's just going around in a circle. To the electron, that circle would be squished, and as it kept, if it were like right here at the edge, can you see where I'm pointing? Can you see that? Or I think I can zoom in. No, it doesn't want me to zoom in. It was sad. As it went to make the turn around this sharp corner, it would see the ellipse rotate with it as it made the turn. Making it complicated to apply the right forces to make it satisfy the turn while the turn itself is changing to the electron. You had to synchronize the shape of the magnetic field the charge is experiencing to the fact that it's seeing this contortion from length contraction. Yeah.
So if that ellipsoid-esque thing is turning as the particle is also trying to turn that corner
to the particle,
yeah. What sort of path does it follow then? Because if the ellipsoid's turning with it, that just seems like it just make another circle, like a.
Well, the thing is, it's not moving at all. What's happening is it is seeing, if you're driving down the highway in your car, you don't see yourself moving down the highway. You understand that the Earth is so large that you don't picture the Earth as moving underneath you. But the reality is, in your reference frame, you're sitting still and you're watching the road move past you. And so, as a consequence, the electron is sitting still. It sees this weirdly shaped thing with this huge electromagnetic field around it, and it sees this tube getting thrust past it and constantly getting bent so that it can cycle through its position.
But would it actually see the ellipsoid? Because, let's say I'm, in a circle running really, really fast. Let's say I'm going as fast as this. That's probably not possible, but let's say I'm running as fast as this. When I look ahead, I couldn't necessarily see all of this ellipsoid, right? Because there's a point in my view where I can't see past the horizon. You know what I'm saying?
Yeah. If it were this gigantic, but if you were running near the speed of light around the track at your school, you would see, like if you were on the long stretch of the track, you would see the distance on that track smashed down to a small value. But you would see the distance across the field to the other side of the track as being normal. It would be very, I mean, what we're all connecting with is that the answer is that if you were to try to travel at relativistic speeds, the whole world would be contorted and twisted and oddly shaped and constantly change with every motion that you made. And if you look carefully on the assignment sheet much later on, you might have noticed there's an assignment that's download and play a slow speed of light. It's a game made by the MIT Game Lab. It's free. It's also, if you're a computer programmer people, it's all open source, and they give you the engine that they use to make it. And what the game is you walk around collecting these orbs. I'm sorry, I'm sick.
Me too.
You walk around collecting these orbs, and every orb that you collect brings the speed of light down lower and lower and lower, making these relativistic effects that we're talking about more and more and more present, or even walking. And so eventually when you collect all 100 orbs, you'll find it becomes nearly impossible to go anywhere. It's so hard to control your motion because not only does it take absurd forces to change your direction, but also the entire world shape changes every time you move. If you're having a little bit of trouble understanding this, I think what you're doing is joining the club. This is very weird. This is the stuff developed by this guy. I don't know if you remember his name. His name is Einstein, and he's kind of famous for being really, really smart and people not knowing what the heck he was doing. So if you're getting the basics of this and starting to get some understanding that this is even a possibility, you're rocking it. You're doing a great job, and these questions you're coming up with are really strong. I am going to want to move forward because I think some of it will answer some of these questions you're asking me. But Henry, I saw your hand. I don't want to squash that. Go ahead.
Oh, I was just going to quickly ask, does that mean in the particles kind of frame of reference, does it feel like it's making a sharper turn than it would be in just a normal circle constantly?
Be careful how I say this. So from its frame, it's not making the turn. The pipe it's going through is making a turn around it. And the answer to that question is yes. It sees that pipe having to make this like abrupt turn to get around it. From our perspective outside, what we notice is that we try to apply a force to turn the charge, and it doesn't turn the way we mean it to. And one explanation of that is like, well, it's experiencing a sharper turn than we think. The better explanation for that is you attempt to apply a force to it, but it experiencing the force is, ready, time dilated. So it takes longer for the force to do what we expect. So we have to push harder than we expect to get it to respond as quickly as we want it to. One of the reasons why we do time dilation first is because every single thing we're going to talk about can actually be entirely explained simply by time dilation. Let's process a little bit. Let's learn a few more things, and it might start to bring some of this together. I'm very happy that some of you seem to be like laughing at me like this is just insane. That's the way it should be. So let's move on a little bit. So to answer Kaylee's question, am I sharing? I am sharing. What we have developed for time dilation and for other equations is this thing, gamma. And gamma is 1 over the square root of 1 minus v squared over c squared. And we have 2 equations that we've generated from that so far. We have that a dilated time is an undilated time, times this gamma factor, and a length that is contracted is the uncontracted length divided by that quantity gamma. I'm sorry, I can't actually write the Greek letter in the drawing program. I mentioned like 8,000 times, I'm pretty redundant about it in the video, that it must seem weird to you that we bothered to call gamma 1 over the square root thing. And what did I tell you was the reason for that? You remember? Yeah, Kaylee?
Because most applications actually use it in that form as opposed to time dilation, which uses just the square root.
Length contraction is what you mean.
Or length contraction.
length contraction has the square root upstairs, and that's the thing that's exactly what's confusing about it. That when gamma's upstairs, the square root's downstairs. And you're right. We're going to have 3 or 4 more equations where gamma, it's going to go this way, and that's why we've chosen to do it this way. So the question that Jasmine posed, was, isn't it true that, let's say that we put, here, let me move the rocket ship to the back. Some girl on a rocket ship and some other lady on a planet who's ginormous, really huge person. And we had the rocket ship traveling, I'm going to do this. The rocket ship traveling forward at some enormous velocity, heading towards the speed of light. And let's say that the person on the planet were bouncing a basketball. Okay? And the person in the spaceship was at the very same time playing with a yo-yo, like bouncing a yo-yo up and down. Super high-tech stuff. Okay? The way that time dilation works is that this person would say that the time for the basketball bouncing up and down is normal or dilated, do you think?
Normal.
Dilated.
According to this guy, the basketball, according to the guy in the spaceship, she herself or he himself is standing absolutely still, and they are watching the planet travel backwards relative to them, like you watching a street sign pass you and head back in the other direction. Is this making sense? So the person on the spaceship thinks she herself is stationary and that the basketball is traveling relative to her. So the time for the basketball should be dilated, and the time for the yo-yo should be
Undilated.
Yeah, we'll say normal. The real word for it is proper. Okay? Now, let's just say that I am calling, therefore, this reference frame on the spaceship K, and the reference frame on the planet K prime. So that means that in contrast, the person standing on the planet should see the time for the basketball as being proper, and the time for the yo-yo as being
Dilated.
Yeah. Okay. Dilated. And so you're, let me get, get my primes right inside there. So you might be saying like, well, how is there any twin paradox possible at all? Like if these two people were twins and one of them hopped on the spaceship and traveled away, they would look back on Earth and see time is dilated on Earth. Earth would look at them in the spaceship and be like, dude, time is dilated for you. What are you talking about? Person in the spaceship would turn around, come home, land, and if they both saw the same thing, shouldn't it all be symmetric and there shouldn't be any difference in all? Everything is done. Right? And there's a problem, well, not a problem. There's something I said that changes everything, and it's subtle. Coleman, what was your question? And then Jasmine?
Oh, I was going to say there's something you said.
Sure.
Well, the person on the rocket ship's coming home, so he's going back into the K prime reference frame.
Mm-hmm.
He's no longer traveling the speed he was when the basketball was dilated and his yo-yo was proper.
And careful. You're very, very close. Even if, how do I want to say this? It's not that he's no longer traveling the speed, because both of them, right? If the guy on planet Earth watches the K-frame travel away, he sees the thing speed up, get to a certain speed, travel at that speed, stop, turn around, come back, let's say at the same speed, stop, and there we are, we're back together. The person in the K-frame looks back at the K-prime frame and sees it not moving initially. It takes off away from the spaceship, speeds up, gets to a constant speed, travels away, stops, turns around, comes back at the speed, the opposite direction again, stops, and they're back together. But you're knocking right at the door of what the difference is between the two. They both look at each other and see them speed up, travel at some constant speed away from one another, slow down, stop, turn around, and come back. But there is one big difference between the two frames.
The time dilation is happening in opposite directions, I guess.
No,
kind of
it's
in
a
a
cool.
way.
It's a cool idea, and you were starting to piece together the elements of it, Jasmine.
Is it like about the acceleration? Because they actually have to stop, and that's where things go wow.
Yeah.
The acceleration.
It is acceleration.
Okay.
Now, there are two principal postulates of relativity, okay? And they're a really big deal. Don't mind that picture right there for right now. This is, in actuality, there's only one. I can spell. This is the first postulate of relativity. I'll mention this in a video as well. The laws of physics are the same in all inertial reference frames. The thing that you don't know is that the word inertial means
Oh, no acceleration.
Yeah.
constant velocity reference frames. Okay? No matter what speed you're traveling, the laws of physics always appear to be the same. So if you're standing next to a train and you see somebody drop a train that's traveling by, you see somebody drop a ball, the person on the train sees the ball fall down in a straight line. They see it accelerate due to gravity. They see Newton's second law held up. They see kinematics properly applied, because they don't see that ball as traveling relative to them. All the laws of physics are preserved. You standing on the side watch the train go by, and what do you see the ball do?
Go diagonal.
It's going.
Not just diagonal, parabola. So you're both experienced completely different realities. One of you is like, that ball went in a parabolic path in the y and x plane, and the other person's like, no, it didn't. It traveled in a straight line. I mean, it accelerated, but it was a straight line. Which of them is right?
Both right.
They're both right. There can be multiple realities. The important thing is that they agreed on the laws of physics. The reason why the person on the embankment said it was a parabola is like, well, I saw the ball traveling forward, and then it started to accelerate down. And so I saw a parabola, and the guy on the train's like, well, I saw it not moving at all, and then it fell straight down. So what they agree on is that the laws of physics are correct. In contrast, if I were sitting on the train and it was stationary, and Dallas is right here, and he's outside, I'm like, bye, Dallas, let's see, I'm going into the city for the weekend, and I held up my keys, okay, and the train took off. The train would need to accelerate. So all of a sudden, my keys would angle up in space, right? As the train accelerated, they would get like fuzzy dice hanging from the windshield of a car, or something like that. They would angle back as the car accelerated forward. And if we looked at it, we'd be like, there suddenly appears to be a new gravitational field, right? That like mysteriously some force came from nowhere that angled the keys back. And me sitting on the train, I'm like, holy crap, the train's accelerating. And I would suddenly know that I'm the one in the accelerated frame. Because Dallas would hold up my keys standing on the embankment next to the train and be like, nope. I would see him speed up away from me. Hey, he's accelerating. he would see me speed up away from him. He's like, hey, he's accelerating. He would look into my frame, see my keys angled, and we'd be like, oh yeah, no, dude, you are in an accelerated reference frame. I would look at him and I would say like, oh, you look like you're accelerating, but it's actually me that's accelerating. And I could tell that I was the one accelerating by testing for that angle. Did that make any sense?
So it's kind of like you can have relative velocities, but not relative acceleration.
I mean, you can have a relative excuse me, acceleration, but the big deal is you can tell when you're in accelerated reference frame.
Okay.
And you can't tell the difference. You can't tell if you're traveling at a speed, but you can tell if you're accelerating. So as a consequence, between these two people, if I go back into the drawing here, as this spaceship comes to a halt, the person inside the spaceship will obey Newton's first law. They'll agree on the laws of physics that way and be like, ah, and smash into the front. Because he wasn't wearing a seatbelt. It was a bad call. Okay? He would look back at the person back on Earth and see that reference frame slow down, but he wouldn't see keys being angled. He wouldn't see this person person's basketball go flying off because of Newton's first law. And you'd be able to tell, like, oh, wait, no, these are different things. The one that slows down and turns around experiences some different stuff. Now, the full treatment of that is brutal. It involves things like differential geometry and, like, complex analysis. And I'm not just saying words to scare you. Like, stuff that is not worth our time to come to the conclusion that time dilation works the way we think it does. It's a very cool thing to work harder on when you have more time for it. But here's the deal. If this, let's say, we'll take the basketball example away. How am I doing on time? Okay. Let us say that this rocket ship traveled from this planet to another planet and that they were separated by a distance according to the K prime frame of 10 light years. Okay, so let's say the two planets were 10 light years apart. Light year is a measure of distance. It's the speed of light times the length of a year, which is a completely comical number of meters that's not worth writing down. 3 times 10 to the 8th times 365.25 times 24 times 3,600 meters. Just no. It's a lot of meters. Let's say that this person were traveling forward at 0.866 C. Why did I pick that? Well, that is when gamma equals 2. Okay? So that means that this thing, 10 light years, we'll call that L prime. My question is this, for now. What is L? I've given you that gamma is 2 and that L prime is 10. What is the distance between the planets as seen by the person on the spaceship?
5 light years.
5 light years. Sorry, I know you had your hand up, Jasmine. You've been rocking it. I'm just going to spread it around a little bit. 5 light years. Good. It's half as long. What's really cool about that is it feels like you're cheating. You're like, the faster I go, I just love saying this, the closer the planet is. Which is so messed up. Like, the faster you go, the shorter you have to travel to get anywhere. To make this really fun, if the person were to travel at the speed of light, what's the distance between the planets?
Like 0.
0. If you travel at the speed of light, the width of the universe is 0. The amount of time it takes you to cross the universe is 0. You are everywhere simultaneously. Good times. Let's not go the speed of light. It seems. How could you have a question? Will, go ahead.
So why does it take time for the light from the sun to get here? light from stars to get to our viewpoint? Like, why does that take time?
So it takes 0 time to the light, but not to us.
Right.
So yeah, that's the weird thing here. So here we go. What is T prime? Now you don't have to do the arithmetic in your head here. How would I find T prime? The time it takes for the spaceship. What's that?
Gamma.
I think the prime is throwing you off. Here, I'm just going to say it. It would be the distance divided by the speed. Right? The person on K prime sees the distance as 10 light years and sees the ship as going 0.866 c. So by the definition of velocity, they see the time as 10 light years divided by 0.866 c. This is old school physics. Are you okay? You're okay with that? That equals, I did the math, where is it? 11.5 years, I think, rounding a little bit. 11.5 years to get to the other planet. Now, what is the time to get to the other planet as seen from the unprimed frame, T? There's 2 ways to do it. There's a really easy way. What's the really easy way? Jasmine, you want to crack at that one?
Is it just multiply by gamma? So just 2 times?
It would actually be
divided by.
Divided by gamma.
The other way around.
Because the event we're talking about is the person leaving and arriving. And so and this is confusing, and that's what the next video is about on proper frames. So I'm going to give you some support there coming up. The person out here in K prime would see that as being the dilated thing, so we would divide 11.5 by 2. The other way to do it, which would be totally equivalent if we think about it, would be to take the length that he sees, 5 light years, and divide by the speed he sees the planet coming at him, which happens to be also 0.866 c, which might be a little weird to you, but right, the velocity is still going to be symmetric here. He sees the planet come at him at 0.866 c, and this would give you a value of time equal to, what is that, 5.8-ish years? Which is half of this, or you could have done it the other way. Whatever way you understand, do that. It's fine. Now, let's say the person turns around and comes back. Weird stuff happens during that acceleration. But in the end, think about it, it's the same trip the other way. What happens to the total time?
Doubles.
It doubles. And you might be like, are you sure? Because I'm a little worried now. And it does. The subtleties of it are, as I said, subtle. So the time for the total trip to this person, that is not supposed to be a superscript, is 11.5 years. And the total trip for this person, the trip RAM, is about 23 years. So Jose takes off from planet Earth, goes to planet Kashyyyk, which is 10 light years away from Earth, turns around, comes back, lands to see his twin brother Jose. Jose B is like, yeah, it's been 11.5 years. It's been a long time. Jose is like, dude, it has been 23 years. What are you talking about? And they are different ages. And this is called the twin paradox, because that can't possibly happen, except, yes, it can. That is what would happen. Which is a huge problem with time travel. Space travel. If you wanted to travel the speed of light to a planet, it would take you no time to get there because the distance would be 0. You would somehow mythically come to a stop at that planet, turn around, come back. It would take you no time at all, and you would arrive back home at the death of the universe because everything would have happened. All of time would have occurred. So don't travel at the speed of light. You probably will miss class, first of all. I mean, there are going to be tests, and that's going to... Okay, I'm sorry. All right. Good. All right, so I'm going to ask a question now, and hopefully it'll get a little bit of laughter, but in terms of practical concerns is what I mean the question for. Are there any questions about the twin paradox? Yeah, go ahead, Jasmine.
Sorry, I just have a question about the whole, if you travel at the speed of light, then all of time happens for you. So, like, is light outside of time then? Like, is it just existing outside of time?
Yes and no. Again, it's a question of reference frame. If you were a photon, if you were the photon, you would be experiencing all of time at once. You watching the photon are not traveling at the speed of light. You experience time, and you experience the photon experiencing your time. So it's a matter of perspective. But I mentioned this last time, actually. There's a good video put out by PBS, not great, but good, called The Ghost Particle. And it was about our attempt to detect the mass of a neutrino. And we were attempting to detect neutrinos at all. And one of the first experiments done was to look at neutrinos coming from the sun and collect them, count them. And we had one experiment in the early 30s or 40s or something like that. Maybe it was 50s. We had one experiment to detect for one of three kinds of neutrinos. And we did the experiment, and we counted 1/3 the number of neutrinos we expected coming from the sun. The sun should have been spitting out this one kind of neutrino, and we were collecting it. We knew how many we should get, and we got 1/3 the number. And the weird thing was there are three kinds of neutrinos. And so what people hypothesized under quantum mechanics, which we'll talk about eventually, is that the neutrinos were kind of randomly transforming into the other kinds of neutrinos on their way here. So that by the time they got here, they kind of randomly distributed themselves as 1/3 the kind we expected, 1/3 another kind, 1/3 another kind, so that we were only detecting the ones that were left. But that would mean that neutrinos weren't traveling at the speed of light, because we saw them experience change. We saw them experience time. And if for them to not travel at the speed of light would require that they have mass, and people thought at the time that neutrinos were massless. And so this meant that they had to have mass, and the guy who did the experiment was shamed and shunned in the physics community until much later somebody did an experiment and was like, oh, dude, sorry, neutrinos have mass, and then they gave him the Nobel Prize. And yeah, oh no, and it's much worse than that. He had Alzheimer's by the time he got the prize, and he only half knew what was happening. It's physics is tough. Coleman.
So if you were to have a lamp, and you turn on the lamp, and the light travels onto a mirror and back, does that mean that according to the light that just traveled, infinite time has passed from my perspective, so nothing exists here anymore?
From the light's perspective, as soon as it was emitted, well, I'm going to get myself in some trouble here, but I don't think I'm saying anything wrong. As soon as it came into existence, it saw the entirety of the universe's life. All of time happened before it. In our perspective, it came in and out of existence in time. One of the problems that we're going to run into here is we're starting to necessarily talk about quantum mechanical objects being created and then experiencing relativity. And quantum mechanics and relativity aren't always the best of friends, which you may have heard. There are some distinct problems with it, and so that's the fact that the photon comes in and out of existence is adding some weirdness to that. But leaving that aside, which is not actually allowed, but I think for our discussion will suit, comes into existence. It sees the universe as having no size. It can't even tell that a mirror is there. It's like, I don't know, I'm a photon, and then it disappears. And we see it woo, bounce back and forth at a very large finite speed. And that's it. So yeah, it sees all of time during its existence and sees no distance to the mirror whatsoever. One of the ways to kind of sum this up, I think, which helps, is people originally thought that light traveled at infinite speed, right? And it took a while for us to realize it travels at just a very large finite speed. And what I'm saying is, to a degree, to the light itself, it is traveling at infinite speed. It travels the entire distance of the universe in 0 time. It takes no time for light to travel the distance to itself. And the reason why is that there's no such thing as a meter. 0 in length. So anyway, that's the easy paradox. Being that we have 10 minutes left, I think it's probably a really good time to bring up the tunnel paradox. So that bundle of joy. I was going to use the Doppler effect to explain something, but I don't have to. By the way, I didn't mention the second postulate of relativity, that C is a constant in all reference frames. What I'll tell you later is that that's actually a law of physics, and that doesn't need to be said. The fact that the laws of physics are the same in all inertial reference frames is enough to necessitate that C is the same. So modern versions of relativity don't include a second postulate of relativity. So the train paradox was this, and I'll try to be quick with it. A train travels into a tunnel, a very well-drawn tunnel through a mountain, and we're standing outside. We see the train as length contracted due to relativistic effects, so that as it travels forward, watch the animation, we see it enter the tunnel, and then the end of it enters before the front ever comes out the other side, right? Because the train is length contracted so that it fits inside the tunnel. Now the train is like, no, that's not right. I'm still my normal length. I'm not length contracted to myself, but the tunnel is length contracted. It sees the tunnel is coming towards it. It sees itself enter the front of the tunnel. It sees the front exit, and then it looks back and waits for the other end to even get inside. That is a much more convincing paradox. If you're not like, what? I would be worried about you. So let me just kind of bring both of these drawings in perspective. What I'm saying is that the two people in the two different reference frames experience these two different realities. One of them experiences a train as and I'll bring this to the front so we can kind of see what's up. Sees the train as fitting inside the tunnel, and the other frame in the train itself sees the train as not fitting inside the tunnel at all. Do you have any questions or problems with that? I usually... Oh, yeah, go ahead, Will.
Well, I mean, obviously there's like questions with it, but so what about for things that have to like talk back and forth? So say like a cell tower and a phone that are talking. Huh? So the cell tower would see the train inside the tunnel, but the phone sees itself outside the tunnel. Like,
thankfully, if the train were traveling at these speeds, the time in the tunnel would be small, right? It'd be going so fast it wouldn't be an issue. But you know, you're right. One of the things one of the pieces of salesmanship I usually put on relativity is people are like, yeah, this is all garbage. And the truth of the matter is that the global positioning system and cell phone towers and satellite communication, they all had problems when the GPS system was first set up because they weren't taking into account relativity. And they had to include relativity in the way that the GPS system talks to each other in order for us to get accurate locations. And the engineers that built the GPS just were like, oh, relativity is not an issue. Nothing ever travels fast enough for it to matter. But the measurements were so precise that it made a huge difference. And until we took into account both special and general relativity, the GPS system didn't work right. And there are issues with cell phone towers and things like that. So, but other questions like that. I'm trying not to. Yeah, go ahead, Peter.
What is the difference between general and special relativity?
Special is what we're talking about right now. Things traveling at constant speed. General is things that are accelerating, and it is hell on earth. It is the hardest mathematical thing that you can do. And I think barring nothing, Einstein had to invent tensor mathematics to do it. And it is Einstein's way of explaining how gravity works. We will talk about it for like a week or two between this unit and the development of the quantum model. But more questions about the tunnel paradox, and if you don't come up with it, I will tell you the questions that I often get, and I'll just make an extra video on it because it's the coolest thing. Maybe even this entire class, it's the coolest thing.
Oh, that's another one.
All right, give it a shot, Will.
So I know we just talked about acceleration, so that might be the answer. But what if the train were to stop in the middle of the tunnel? Would it would it span back into the tunnel?
There you go. So that's very much related to it. These are the two questions I remember most. What if there were like lasers? It's always lasers. What if there were like lasers at the edges of the tunnel? And they're set up so when the front of the train reaches the far side, a gate snaps shut and closes so the train can't get out. And that when the back of the train passes into the tunnel, the gate over here, let me see if I can do this, a gate snaps shut here. So that in one reference frame, this gate would have snapped shut, but the back one wouldn't have gotten a chance to snap shut yet. Oops, I'm not drawing. Here, I'll do that. In this reference frame, the tunnel trapped the train. And in this reference frame, I don't know what the hell happened. And the other version of the question was, what if somebody was standing on the front of the train and the back of the train? One of them had a water balloon full of red paint. The guy in the back of the train had a water balloon full of blue paint. When the guy in the front, guy in the front comes out the end of the tunnel, he's supposed to throw the balloon right here to the center point of the tunnel. When the guy in the back enters the tunnel, he's supposed to throw the blue one. So in one frame, in this frame, the red balloon, the one from the exit of the tunnel, should get thrown first. Splat, red paint. Then as the back of the train comes in, the blue paint should be thrown. Splat, blue paint on top. In this reference frame down here, the back of the train enters first, right? So blue paint, splat, and then the front comes out, red paint, splat. Which one's right? Now the answer to the paint question is you are completely ignoring the fact that relative velocity is an issue here. The fact that throwing the paint backwards would make a difference, would change the velocity of the paint. And there would be one answer. And you were just ignoring the fact that the relative velocity of the paint is going to be affected by this process. Okay? The fact that the train is traveling forward when the blue paint was thrown forward is going to mess with things, and the fact that the red paint was thrown backwards is going to mess with things. And we haven't taken that into account. And if we took it into account, everything would agree, and one of them would be right. But then the person who asked me the gate question is like, yeah, but what up? Aren't they all dead? Or are they trapped? What happened? Henry.
For the throwing the balloon thing, couldn't they just drop the balloons instead, and then the question would be which balloon hits the ground first?
Yes, absolutely, and that's a good point. And the answer to the question, and I think I'll start next time with this, is that that is different in different reference frames. Simultaneousness is, and you might remember in the older videos, I'm talking about are these events at the same time? And the answer, even if we were just standing still, you remember that in one of the really early videos? You could be standing somewhere where you see two lights blinking at the same time and just stand somewhere else and not even move and see the lights blinking at different times. Simultaneity is broken by relativity, even without Einstein. Okay, so simultaneity is out the window. And this question with the gates is actually a simultaneity question. Yeah. Okay, Peter.
Okay, for the
Go.
paint, what if you pressed a button and the paint just appeared on the floor, and that other person pressed a button and his paint appeared on top, and like whoever pressed the button first would have his paint on the bottom?
Yeah. Again, even there, the information has to travel from the button. Okay? And the velocity of the electrons in the wire carrying the information, or the apparent length of the fiber optic cable that the light traveled through to send the information to get to the device that spat the paint out, all of that matters. And that, like, the length of the wire to send the message would be different in a different reference frame. And it would all work out so that one answer is correct. The gate question, though, I think sums it all up because it's the same question. And I'll just say, I had a student last year, someone you know. I had a student, and I'm doing a fairly good impersonation. This is Angus. Angus, what? And he's like, if the front gate slams shut, I'm like, yeah. Doesn't the train hit the gate? I'm like, yeah. So doesn't the gate exert a force on it? Yeah. So doesn't the gate slow it down? Yeah. So doesn't the train smash into the wall and slow down? And as it slows down, it sees the tunnel. It actually smashed into the gate. And as it smashes into the gate, the length contraction goes away. And it watches the far side of the tunnel expand away from it and snap shut on the other side. Yes. And so I think it's probably good enough. We'll talk a little bit more about the tunnel thing because it's like the coolest thing that's ever happened ever. And if you're like, my world nothing is okay, and you're walking and afraid to open doors or like getting in the car, like that's where this is supposed to go. It's gonna get easier on your heart and mind and soul a little. But my ultimate dream, and the thing that I always hope for this course, is that you'll understand a little bit of what we're talking about. You'll be able to plug and chug the equation and scare the crap out of some professors in college. You'll be like, how do you know this already? But the real goal is to make you think this is the coolest thing you've ever seen and want to know more. Because you can understand this on a very concrete level, and it will make sense to you, but it takes a very long time. But we'll keep digging next time. I got to catch up on videos, so now I got to make an extra one. So I will see you on Friday.
Right.
Thank you, everybody.
Thanks.
Bye.
See you later.